Okay, so last we left off, we had talked about how to work with the concentrated volume and to dilute down to a lower concentration, right? And so the easiest way of doing this is using C1, V1, and that's going to be equal to C2, V2. So C1 is going to be equal to the concentration. Concentration of our stock or our first solution. V1 would be the volume of the stock. C2 is going to equal concentration of our dilution. And V2 would be its volume. Okay, so here in this problem, we're basically going from a stock solution and we're trying to make a diluted version of this. How many of you guys have drank Kool-Aid before? Anybody? Okay, so we know that Kool-Aid is an example of having a concentration, right? It's concentrated. And now they have little squirt bottles of Kool-Aid that we can use. So we can use that concentrated version to make our normal drinking version, right? And so this is going to be a very similar process. So the way that we're going to do it is that for our stock solution, we're going to go ahead and measure out our stock solution. So we're going to assume that we have 100 mils of 0.100 molar K2 CR to OSET. Okay, and so we're going to dilute this into a volume of 1,000. Okay, so here this is going to represent our V1. This here is going to represent our C1. And as I told you, we're going to dilute it to a volume of 1,000. Okay, so in the case of us having 1,000 milliliters or a liter, that's going to represent our V2. So we need to calculate the new concentration now that we're doing a dilution of it. Okay, and so the way that we would do that is by using this equation. Okay, so we'll have, I'm going to rearrange it. So we'll end up with C1 V1 equals C2. Then put the V2 over here. Okay, so then what we're gonna do is we'll plug in everything into our equation. Zero, zero, molar times 100 milliliters. And we're dividing that by 1,000 milliliters. Okay. So then we're going to get a volume of our V2. I mean, our C2 is going to be 0.0 100 molar. Now, if you take a look at what's happening in the pictures, so we take our concentrated solution, we're going to dump it into the 1 liter flask or the 1,000 milliliter flask. So then we're going to bring it up to solution by the addition of water. So when we go through this process, the first thing that we want to do is rinse off our the device that we actually use to measure the initial 100 milliliters. So this here, let me sort it out. Can you guys see my spotlight? So this here is called a volumetric flask. It's set up to get exactly 100.0 milliliters of solution. Okay, so we take this 100 mils of our 0.1 molar potassium dichromate solution, and we're adding it to the 1 liter volumetric flask. So then we take our water bottle, we're going to rinse out after we pour this in here, we're going to rinse out the remainder to make sure that we have all of the solution. We're going to put the wash into that bottle as well. And then we're going to bring this volume up to exactly 1 liter. So then that way we know exactly the concentration that we're adding. Okay. Okay, so our question is, how many milliliters of a commercial hydrochloric acid, how many milliliters of commercial hydrochloric acid, which is 11.6 molar, should be used to prepare 5.50 liters of a 0.500 molar hydrochloric acid? Okay, so what equation are we going to use? So you guys are going to have to respond because you guys are the class.
C1 V1 equals C2 V2.
Adele, can you speak? Can you say something?
Yeah, can you hear me?
Yeah, I can hear you now. Yeah.
Okay.
So what are we going to do here, guys? What equation are we going to use?
The one you just showed us, right? Is it C1 V1 over V2 equals C2?
Okay, so in this case, are we looking for C2 or are we looking for V2? Because it asks us, it says how many milliliters? Milliliters is what type of unit? Is it mass? Is it volume? Is it concentration? Is it length? Is it don't all you guys yell at me at once?
Volume.
It's volume. That's right. So we know it's volume. So we're looking for the volume. So we're in this case, we're going to be looking for V2, right? So we're going to rearrange our equation. We're going to start off with our general equation. C1 V1 equals C2 V2. And then we're going to solve for V2. So in this case, we're going to put our C1 V1 over C2. Then that's going to equal our V2. Okay, so what is our C1?
That's concentration.
The concentrated acid, that's right. That's going to be concentration. So it's going to be the very first one that we see here. So that's going to be that 11.6 molar. So we use the M to represent molar. What is our V1? Oops, my bad. Okay. Telling you guys wrong already. So here we're calculating for V1 because we're trying to figure out how much of the commercial hydrochloric acid that we're adding, which is the concentrated one. So we want to solve for V1, not V2. So let me modify my equation. So V1 is what we're trying to answer. We want to figure out what it is. That's a big question. Okay, so then our C2 is going to be, what is the other concentration? Feel free to type if you can't talk. Okay, now remember it's concentration. So we know that milliliters is going to be volume. So look at the problem. What is going to represent concentration? So for a C1, we know that it was 11.6 molar, right? So then what must be C2?
It's 0.500. It's the other molar.
That's right. And then our V2 is going to be
Liters. 5.50.
5.50 liters. Okay, so then now all we have to do is plug everything in. V1 is going to be equal to 0.500 molar times 5.5 liters divided by 11.6 How many sig figs should we have?
Two.
Are you sure?
Oh, no. Three.
We should have 3. Yeah. So this would be liters, so to change this into milliliters, then we have to multiply this by 1,000. So 0.237 liters. We know that we just multiply this by 1,000. Okay, questions? Concerns? Cash? Okay. Let's move forward. Okay, so when we're working with concentrations, right? We know that we're talking about moles over liters or quantity over liters. Okay, and so this is going to kind of help us in the long run to understand that we can sit there and use the molarity to sit there and do it. When we're talking about stoichiometric problems in general, we're working with moles. Okay, and so we want to make sure that we're starting out with moles. And so if we know that number of moles, we use the symbol N for the number of moles, that's going to always equal that concentration, that C1 times the volume. Okay. This is where N is equal to moles. C1 is equal to the concentration. And V1 is equal to volume. Okay. So if we're given the number of particles or atoms or molecules, we know we're going to use Avogadro's number to get to the number of moles. If we're given the mass, we know that we're going to use the molar mass to get to the number of moles. If we're given the concentration, we know that we're going to use that volume to get to the number of moles. Okay. So this is just basically telling us what we just talked about. And this is taking everything in consideration that you've learned up until this point, except for gases, which we'll be talking about later. So we've talked about energy. We can apply energy in this case. We've talked about mass, which we can use the molar mass to sit there and get there. We've talked about concentration, and then we can use volume to get to the number of moles. Once we get to the number of moles, we can use the chemical equation, a balanced chemical equation, to sit there and get us to how much product there is. So I have a question because I had a group of students that gave a presentation. Somebody asked them, so what is the purpose of balancing chemical equations? Why do you need to do that? What does the chemical equation represent? Anyone?
Changes or processes?
Changes the processes.
Yeah.
Okay.
So when something combines with something and it becomes something else.
Okay. Can you give me a real life analogy that we use daily that can help us understand the concept of a chemical reaction? Maybe not daily, or
If you leave your bicycle out in the rain, the damp will cause the chain to rust. But if you protect the chain with oil, it will slow down the effect.
Okay. That's good. So that's a good analogy of a chemical reaction. But can you give me a good analogy of a balanced chemical equation?
I'll take a guess. Fireworks that haven't been ignited yet.
Fireworks so would that be an example of a balanced chemical equation?
That they are sitting in a balanced form, and then we do something to change that balance, which causes the explosion.
Okay, but are we talking? So let's get into the nitty gritty here. So is it 1 or 2 fireworks? Is that going to yield 7 fireworks or 7 explosions? Or is it? Do you understand what I'm saying? So
No, it's not going to perpetuate now.
Yeah. So
It'll just do the one.
can you give me an example in real life that you guys do every day where you're using a balanced chemical equation? Anyone? Stephanie? Breathing? Okay. So breathing. That'll work. So what happens in the case of breathing? Alexis?
You breathe in oxygen and then you produce CO2 on the way out.
Okay. So show me how it's balanced. Like, how many of you guys cook? I'm just curious.
Yep.
Okay, how many of you guys cook using like box stuff or like box cakes or hamburger helper?
Definitely.
Okay, it's gourmet meals, right? Okay.
Yep.
So if you think about that, what are the instructions back there in the back?
Well, it gives you a list of your products, and it gives you the order to assemble them.
You mean your reactants, right?
Okay. Yes. Yep.
At the end of the day, right?
Yep.
So if we're talking about a hamburger helper, right? It's the ground, it's the noodles that are in the packet, and if you think about it, it's giving you the quantity of it, right? It's 1 packet of noodles, right? It's a pound of ground beef. It's, so if we follow any recipe, you basically are doing a chemical reaction, right? Because this plus this is going to yield this. And this is what you're getting. You're getting a dish of this, right? So if you think about it, every day that you're in the kitchen, you're following a chemical reaction. Now let's say, let's say hamburger helper, right? Because when I'm in a tight crunch, that's what I use to feed people. Hamburger helper, it's gourmet meals, right? So let's say I have 30 people coming over, right? And on an average, I'm going to say a box of hamburger helper feeds about 3 people. Can I use that equation to sit there and calculate how much I'm going to need to feed 30 people?
Yeah.
Yeah. So a chemical reaction is just like that recipe that we use to feed our families, right? If we have more family members coming, we can scale up. If we have less family members coming, we can scale down, right? Let's say it's just me. I don't need a full box of hamburger helper. Well, maybe I do because it's not a lot, but so we can make the adjustments accordingly, right? And that's exactly what happens in the case of a chemical reaction. Are you guys with me? And so if you think about it, a chemical reaction is kind of like a recipe. Okay. Okay, so now let's use this concept of volume or molarity to help us sit there and solve a couple of equations. Okay, it says calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide all of the copper ions in 30 mils of 0.635 molar copper 2 sulfate. So what do you guys think is going to be the first thing that we need to do?
I'll write the equation.
Okay, so we're going to write the equation. Okay, so what are my reactants? Says calculate the volume in milliliters of a 0.842 molar sodium hydroxide required to precipitate. Okay, so my first thing that I know that I have is going to be sodium hydroxide, so that's going to be one of my reactants. So what is the chemical formula for sodium hydroxide? Anybody? You can type it in the chat if you can't talk, if you're at work or if you're busy with children. Sodium hydroxide.
Was it NaC? No, NaHO? I'm just taking guesses because I can't find it on my chart.
NaOH, yes. Okay. Now we know that this is going to be a solution because they're giving us concentration. So we know that it's been dissolved in water. So we're going to make it aqueous. Okay, and then it's going to be reacting with, so we know that we're precipitating copper 2 hydroxide. So that's going to be our product. Okay. So then the copper 2 sulfate must be our other reactant. So what is the chemical formula of copper 2 sulfate? Anyone? Now remember, it's all hard nail now, so this is your class. So.
CuSO4 2 minus?
It's going to be CuSO4. We know it's not going to be 2 minus. We know that the SO4 is a 2 minus charge, but we also know copper is a what charge? Because it's copper 2, and we know the Roman numeral always represents
The charge.
charge.
Positive. Yeah.
So then we know that there's no charge at the end of it, so we don't want to put that in. Okay. So we also know that this is a solution because they give us the molarity again. So we're going to put AQ. Okay. So we're going to yield. We're going to yield on the other side our product, which we know is a precipitate. It's going to be copper. It's going to be copper. Okay. It's gonna yield the copper 2 hydroxide, right? Oh, thank you. Okay, now since they say it's precipitant, what does that mean?
It's a solid.
That's right, it's gonna be a solid. Okay, so then what is gonna be the other product?
It's gonna be Na2SO4.
Okay. And I'm gonna tell you guys this, and hopefully you guys will remember it. Anything that is in group 1 is always gonna end up staying aqueous. It's not gonna form a precipitant. Okay, so group 1 metals are always gonna be aqueous. They're never gonna form a precipitant. So this is gonna be aqueous. Okay, is this balanced?
No.
Okay, so what do we need? Balance it.
You need to put a 2 on the reactant side on the NaOH,
Okay,
and that balances you out.
okay, so now we have a balanced chemical equation. Okay, so this makes it a little easier to work with. So the next thing that we need to do is we need to get the volume of, so we're looking to try to get the volume in milliliters of the sodium hydroxide. But first, we need to figure out the number of moles because we have to start off with the number of moles to be able to get to that volume. Okay, so we know that we have 30 mils of a 0.635 molar copper 2 sulfate. Okay, so 30 mils. We know that molarity is what units again? You guys remember? I'll help you guys out. So that M represents
MOL.
M represents moles over liters, right? So that would be what the units are for that. It represents moles over liters. So if we have 30 mLs, 30.0 mLs, the first thing that I want to do is convert that into liters so that the units match up. Okay, so then in this case, I know that 1 liter is equal to 1,000 mLs. So my mLs are going to be able to cancel out. I should probably say copper 2 sulfate. Okay, so then now I can use my molarity, right, to get the number of moles. So I know that M represents moles over liters. So then in this case, I can put my 0.635 moles over 1 liter. Okay, so then my liters are going to cancel out. And now I can use my chemical equation to sit there and determine the number of moles of the sodium hydroxide I'm going to need to react with. Okay, so I know the ratio of sodium hydroxide is 2 to 1. Right? We know that that's understood to be 1 there. So for every 1 mole copper sulfate, I have 2 moles of sodium hydroxide. Okay, so that gets rid of moles of my copper 2 sulfate. And now I can also use the molarity of my sodium hydroxide. 0.842 moles of my NaOH. And we know that that's going to be 1 liter of NaOH. And we want milliliters, right? So then drag this over. Can you guys see all my writing? So we know that 1 liter is going to be 1,000 milliliters. Okay, so if we do all the math, so multiply across. Okay, so that's going to equal 45.2. NaOH. Okay. Any questions? Does this start to look a lot like chapter 3? Did everybody get it down? You need a minute. Okay, let's move forward. So when we're in lab, we often will use what we call a burette to do titrations. A burette basically, it holds the volume of the liquid in there, and it's a graduated piece of glassware, so that we're able to sit there and determine how much our starting volume is and how much our ending volume is. And so by taking that difference, we're able to determine how much we added to neutralize or to titrate our sample. Okay. And a lot of times we'll also use an indicator to help us get precision for that titration. This is an example of burette. So it's here. And so the burette basically has this little valve that we turn, and it's allowing the solution to drip through. And then if you take a look at our solution has an indicator. So it actually turns pink when it gets to the concentration of the solution that we want in there. So a lot of times this is based upon pH, or it could be based upon the addition of a particular chemical to cause that color change. Okay. So when we're doing titrations, we're going to be using molarity. And so we have to standardize our instrumentation to make sure that everything is appropriate. Standardization is just to determine the concentration of solution that is going to be used for titrating a sample, okay? And then we typically are going to start off by doing this with a standard, a primary standard. So something that we already know what it is and that we've used a couple of times to make sure that we can get a nice curve and to be sure that our titration, our titrating is what we want it to be. Okay, so here we have 25.0 milliliters of a sample of an electroplated solution is analyzed for sulfuric acid concentration. It takes 46.8 milliliters of a 0.661 molar sodium hydroxide to neutralize the sample. So we know that sodium hydroxide is acting as a base, and it's going to be neutralizing our acid, which is sulfuric acid. So find the molarity of the sulfuric acid. Okay. So what do you guys think we're going to do? Any guess? Okay. So the very first thing that we're going to do in this case is, so there's a couple of things, right? We can write the chemical equation. So we have sodium hydroxide, and it's going to be reacting with sulfuric acid. We know that this is what type of reaction?
We're looking for double reaction,
So double displacement? Yes.
double display, yeah, sorry.
So we know that the hydrogens are gonna hook up with the hydroxides, and then that's gonna basically form water. And then the sodium is gonna hook up with the sulfuric acid, the sulfate.
Dr. Henry,
Yes.
what happens to the extra H in OH? When it
There.
becomes water.
Now, when we look at it, remember, it's just, we're looking at one H. Even though that this is superscript, right? Subscript. Even though that this is subscript, we're only using one of those H's to match up with it. There's two of them,
Oh,
but we're only using one for this case, right? So that's going to bring us to our next question. Is this a balanced chemical equation?
no.
No. So what do I need to do to balance it? Okay.
You would start off by putting a 2 there.
Okay, so now it's a balanced chemical equation. Okay, so now we have a balanced chemical equation. So this is an example of a neutralization reaction because we're getting water, essentially. Okay, so in this case, we know that the sodium hydroxide is going to be used to neutralize what we're looking for. We know that the ratio of the sodium hydroxide is going to be a 2-to-1 ratio. For every 2 sodium hydroxide, we only need 1 acid, one of the sulfuric acid. Okay, so that's going to be important for us later on. So the first thing that we need to do is go from milliliters to try to get to moles. Okay, so the way that we're going to do that is we're going to change our milliliters into liters. Again. Because we know that molarity is moles per liter. Okay, so how many milliliters are in a liter?
1,000.
Okay, so then milliliters are going to cancel out. We're left with liters. And so now we can use the molarity, right? Because we know that that's really moles per liter. So then we have 0.661 moles of NaOH. And that's going to be over 1 milliliters are going to cancel out. So what is the molar or the stoichiometric ratio between sodium hydroxide and sulfuric acid?
Two to 1.
It's 2-to-1. So for every 2 moles of NaOH, we have 1 mole of H2SO4. Okay, so now we have moles. We need to calculate our moles. Okay, so we're going to end up with 0.015. How many sig figs do we have? That's right, 3. 3 is correct. Moles of H2SO4. Okay, now that we have the number of moles of H2SO4, they want us to calculate the concentration of that acid, right? Or the molarity of that acid. So then we just need to divide it by the number of liters. We know that we have 25.0 milliliters. How do I change that to liters? I'm going to divide it by what?
$1,000.
Okay. Okay, so then that gives me my liters, and I know that my molarity is going to be equal to moles over liters. Which in this case is going to be 0.0155 moles over 0.025 liters. Okay, and then that's molar. Just have 3 sig figs, my bad. Okay, questions, concerns? Cash, Kool-Aid, crypto. I don't want crypto, never mind. Okay. Did everybody get it down? Anybody need a little more time? Anybody want to give me $3 million? Anybody want an A?
Definitely.
Oh. Okay. Okay, so that's finishes chapters 7, 10, and 16. Okay, so we're gonna start on chapter 9, but I think we need to take a 5-minute break to relax our brains. And then we'll get started. And I think we may be able to finish chapter 9 or most of chapter 9 today. Okay? Okay, so I'll see you back in 5 minutes. Go take your potty break. Okay, so do you guys mind if we do one of the questions from the 3rd exam? Yes, no, maybe? Well, if you guys mind, I'll turn it off so you guys don't have to watch it. Nobody's saying anything. I guess I'll just turn it off.
Chill.
Let's do them.
Let's do it. He said, let's do it. Yeah, let's do it.
Let's do them all. Just kidding. Unless y'all want to.
Okay. So 9C says. Nine says, in the
This is number 9.
Yes. Jerry, are you okay with them sharing some of your answers?
Yes, fine.
No, I don't want to. If I get just the answers on paper, then I get zeros. Okay. So the first part is to determine, or they determine the chemical equation. It says in the lab exercise, you did an experiment where 67% yield of the precipitant, 300. Okay. 300.0 milliliters of 1.00 molar ammonium phosphate is used to dissolve with 50.00 grams of copper 290. Okay, so what are my reactants?
Ammonium phosphate and copper 2 nitrate.
Is chemical formula for ammonium nitrate. I mean ammonium phosphate. Sorry.
NH4 times 3.
Okay.
And then the phosphate is PO4.
Solid, liquid, gas, or aqueous. Milliliters. Molarity. So it's a molarity.
Aqueous.
Plus Copper 2 nitrate.
It's CuNO. 2 times 2.
Cu times 2.
Oh, nitrate. Sorry, 3.
Okay. And it's being dissolved, right, into that solution. So we also know that's going to be. Okay, what do we make? What type of reaction is this?
The double displacement.
Okay. So who hooks up with okay.
Your anion switch place.
Okay. So the other side we have ammonium nitrate, right? Can you see if you could shift the control so it slides over a little bit?
From your laptop?
On the iPad. Yeah, it'll say camera control.
Oh.
See if you can move it over a little bit.
Going?
Yeah, keep going. See if it moves.
Oh, other way.
Yeah, the other way, yes.
Talk to God.
All right, now shift everything over. Cool. Come on. Okay. Is it balanced? Is it balanced? You can answer, Jerry. You want to favor?
But no, it's not that.
No, it's not balanced. What do I need to do to balance it?
I'm a free that. That's right.
Okay.
Copper, that's just one.
Right over here.
This one over there. The other side is 3.
Okay.
Phosphate.
Okay.
Phosphate. Or is that just one? That's one.
Okay.
And then this phosphate has 2.
Okay.
And that one has 1.
Okay.
That one has 1.
Okay.
So for the copper, 1 times 3, right? So for 3 on that side.
Okay.
And then for the phosphate, 1 times 2. 1 times 3 again. Right?
Where?
On the, nitrate, what is NA? Yeah, what is that, right there? Ammonium. So ammonium would be, you need 3 on this.
This is one full package.
But you see how it's a 3 and then a 1 right there? What do we
Oh,
have?
wait. What do we have now?
Oh. Times 2, oh, 6.
Here.
2 times 6.
Then what do I need on the other side?
Yeah, you got the same country class.
Right, so what do I need on the other side? You said there's just one here. These are good, right? So what do I need to do? That's what I was trying. Okay. Okay. So that's part A, right? Anybody want to argue about it? Want to fight about it? Want to give me $2 million? Okay. I take that as a yes. $2 million, right? Okay, so now that we have a balanced chemical equation, let's try to answer the next part of the question. It says, calculate the actual yield of the reaction. Okay, actual yield. I'm gonna erase these numbers. Everybody got them down? Good. Hard to Okay, so my given says that I have so I have 2 values for my reactants. What is the first thing that I should think about since I know that I have 2 values for my reactants? So I know that I have the number of moles for my ammonium phosphate, which I can calculate. Let's go do that right now. It's not calculating. So I know I have 300.0 milliliters of ammonium phosphate. You know that 1,000 mils. One here. We know that our concentration is 1.000 moles per 1 liter. Okay, so that's how many moles of my ammonium phosphate I have. Can I calculate the number of moles of calcium? Copper, 2 nitrate. You got that wrong.
I got 0.15
0.55, let's go somewhere.
of the cup.
300 times 1.00.
I did so 300 milliliters. Yeah, and I got 1 liter, which equals 1,000.
So, yeah, so 1 liter over 1,000 liters.
And then
Milliliters cancel out.
and then 1.00 moles.
That's
in
right.
each
That's-
ore.
That's our concentration, right?
Yeah.
Yeah. Concentration, okay. So then that's gonna equal 0.300 moles of ammonium phosphate. So that's what we're starting out with. Okay. So but we also have this guy, which is our copper 2 nitrate. You guys remember when we talked about the bread? Yes. Cheese sandwich? Yes.
Oh, yeah.
Okay, so if I have, I'm gonna say this, so 2 slices of bread and 1 piece of cheese make a cheese sandwich, right? So if I have 15 slices of bread and I have 5 slices of cheese, how many cheese sandwiches can I make?
Wait, yeah. We have 15 breads and 5 cheeses.
Write this over here. So I have 15 bread, 5 cheese. And we know our reaction is 2 breads
For 1 cheese,
plus 1 cheese
1 sandwich.
equals 1 sandwich.
You got 5. But it's gonna be extra bread left over.
That's right. And what did you just say?
Extra bread.
So we have extra bread left over, right? So when we know that we have 2 reactants, so in this case, we have 2 reactants, right? We know that one of the reactants are in excess or left over, right? The other one is limited, meaning that it will run out before the other thing. So here we have 2 reactants. One limiting and one in excess, potentially, right? So we need to figure out which one is going to be limited. So the first thing that we had to do was figure out the number of moles for the first one. So we also need to figure out the number of moles for the second. So how do I figure out the number of moles for my 50.0 grams? 0 grams of copper to nitrate. What am I going to use? Get the number of moles. What am I going to use to determine those grams and what? Fine, what am I going to use to find my molar mass?
You have to convert grams,
Grams to what?
liters, I think.
Oh.
Millimeters.
No,
Mole?
keep guessing. What's that?
Isn't it to mole, grams over mole?
Yes, we need to get the molar mass, which is grams per mole. So how can I find the number of grams per mole? The periodic table, that's right. Okay, so we know how many coppers do we have?
1.
Have 1 copper. Okay, how much does copper weigh?
63.546.
Said 53.546,
Yeah. 63.
63. Okay, and then nitrogen. How many nitrogen do I have?
2.
I have 2. Okay. And how much does it weigh?
Nitrogen.
Is it 28.0128 or 24? Sorry. Oh, well, if you multiply it by 2, that's hard.
If I multiply by 2, so each one is 14, right? Roughly. So altogether, that's 28. How many oxygens do I have?
Six.
6, right? Okay, so then 6, how much does oxygen weigh?
16.
16 times 6.
86.
Here's 86.
96.
96.
Like,
Sorry, I didn't speak into my mic.
Okay, so we add them all together. You guys have to say every day. I calculate.
187.546.
Okay, so we have 187.546. So we have grams on top. Grams should go on top or on bottom. Grams should go on the bottom. So we're gonna put moles on top. And then copper. Okay, so what are we trying to find the answer for anyway? I forgot. Oh, my hair is getting gray. What is our precipitant?
The ammonium phosphate.
Okay, the ammonium phosphate. Is that our precipitant? Copper phosphate is our.
Oh,
Okay,
okay.
so we want to compare our copper nitrate to our copper phosphate to determine how much we're making. Okay, so what is in our chemical reaction? What is the ratio of copper nitrate to copper phosphate?
3:1.
3:1, that's correct. So for every 3 moles of copper nitrate, copper 2 nitrate, we have 1 mole of copper 2 phosphate. You guys don't mind if I leave it in moles, right? Excellent. Okay, so then that would give me, go to the heavy lifting for it.
Where he got the 187.5?
I
I got 180. I think it's because I rounded it.
Yeah, that's fine.
So that's fine.
Yeah, that's fine.
Okay, so from there, I got 0.0887.
0.0887.
Copper phosphate.
Okay. So if we take a look at this guy, right? So we have, come back to this one. 0.300 moles of ammonium phosphate. Really pushing that bottom line. Okay, so in this case, what is the mole ratio of ammonium phosphate to copper 2 phosphate? What's the mole ratio?
The 2-to-1.
Okay, it's 2:1. That's right. So remember,
Wait, Dr. Henry, how did you guys get 0.0887 moles? I actually got 0.0888.
Did I screw up there?
Or me, or I,
Did you say?
because remember, I they
I
got
don't
one.
know, but what was your number again?
It was 0.0888.
Was that your number? Number you gave me?
Yeah, mine point 0887.
Right.
I got 0.088867.
Yeah,
Okay, so tell me again, you said you got 0.088886.
87.
So 3/8,
Yes, it was 3/8 for me.
and you got 2/8 and a 7. You got 3/8.
I got 2 8s and a 7.
2/8 and a 7. Okay, so in all honesty, it ain't gotta make that much of a difference between the two numbers, right? So you got 0.00887, so then that's gonna be 0.0089. Okay, so then that's fine. In the grand scheme, it's not gonna make that much of a difference. That last number is not gonna make too much of a difference.
The lab just blew up. GG.
So you say won't make that much of a difference, is that because of the significant figures? So
Yes, yeah, same things. Yeah, so if the number after that is greater than,
So it went up.
yeah, when, okay. So. Okay, so next part. Okay, so we're talking about moles. Ammonium nitrate. Ammonium phosphate. And moles of copper phosphate. Okay, so those are going to cancel out. And we're going to be left with okay, so let's look at the two numbers. We have 0.0889 moles of copper to phosphate, and we have 0.150 moles of copper to phosphate. Which one is a lower number?
Isn't it Cu3 parentheses PO4 parentheses 2?
That is correct. So which one is the lower number?
Wait, between what? What's the numbers?
Let me box them. We have for underline them in green. This number here, or this number here.
The 0.0887 is smaller.
Okay,
than two.
so since it's smaller, that means that that's going to be our limiting, right? So that means that the copper nitrate is limiting. This guy is limiting. Okay, now since it's limiting, this is the maximum that we can actually make, right? So this would be the maximum that we can actually make, that smaller number. Okay, so this would give us how much we could make ideally. Okay, so this would be my ideal yield in moles. Okay, so then my actual yield is going to be what? It says you did an experiment where 67% yield of the precipitant. So what do I need to do to this number to get the actual yield?
Do we have to divide it by itself?
Yep.
You multiply it?
Multiply by what?
The percentage?
We multiply it by the percentage. So we take this number, 0.0887. I'm sorry, 889. My bad.
67%.
Yep. moles times 67%, which is decimal form is 0.67. This is going to equal our actual yield. Is that? Yeah. Okay, you get it.
0.0595.
0.0595.
But there's a 6. Wait, no, wait a minute. That's unfortunate.
So 360. So
So in reality, that first 0 won't even matter, right?
no, this first zero always matters because it's a placeholder. Placeholder, and then go to the numbers. What's the last number that's yeah?
63.
So it's 6.3.
Yeah.
So then we take this number and we round up, right? Yeah. So then it should be 996 moles. Copper to phosphate. Okay. So this would be our actual yield in moles. Does it say mass? It just says calculate the actual yield, right? That's part B. And I'll accept it since I didn't tell you. I'll accept it in moles or in mass. So if you want to put it in mass, you multiply it by the molar mass. Okay, questions? Any questions so far? Okay, so here's the next part. It says if the precipitant is completely removed, so we're taking out all the precipitant, calculate the concentration of the other product, assuming the remove of the precipitant and the addition of copper to nitrogen. Okay. So what's left over? What's left over? What was it excess? If the copper nitrate was limiting, then what was in excess? What was the other reactant? What was in excess?
Ammonium phosphate?
The ammonium phosphate. Okay, so how much is going to be left of the ammonium phosphate? What is the mole to mole ratio of the ammonium phosphate to the copper? To the copper to phosphate.
A 2-to-1?
So we know it's a 2-to-1, right? So, in other words, if it's 2-to-1, we know exactly how much we use, right? That's fine. If I put it up here, I put it in a different color. Can I erase my bread and cheese? I know it looks tasty. Okay. Now, the thing is that we know that only 67% was actually used, right? So this is the number of moles that we actually use. Okay, so that means that we need to use this to determine how much is going to be actually used and also determine how much is going to be left over. Okay, so we're going to use that 0.0596 moles of copper 2 phosphate. You told me the ratio was again?
2 to 1.
2 to 1. One mole of our copper 2 phosphate. Yeah, 2 moles of ammonium phosphate. Okay, so then this tells us how much ammonium phosphate that we actually use. Do the calculations for me. Do the heavy lifting for me. 2 times 0.0596.
It's 0.1192.
0.1192, so then 0.119. And 4. Okay, and then that gives me the number of moles that I actually use, right? Number of moles that we actually use. Okay, so we know that we had a total number of moles of, starting out, 0.300 moles. So we're gonna go 0.300 minus 0.119 moles. And we're going to divide it by 0.300 liters. This is going to be our concentration. Or our molarity. So can anybody do that heavy lifting for me again?
I got 0.603 infinite.
Okay.
I got the same.
0.06.
No. There's no 0 after the decimal.
Okay. You got 0.603.
603.
Okay. And that would be of our ammonium. And this is part C. Okay. Questions? Concerns? Cash? Kool-Aid? Rum and Coke? Not too hard? Just long?
That's like 4. I think it's 6.
Okay. How's your brains?
Pretty fried.
Pretty fried. Okay.
That's
Next.
Guys ready for the next part? Let's see. If I could get a screenshot of this. So did everybody already have that answer? We were just wasting time, right? For this one?
Yeah.
Everybody already had this, right?
Yeah, I thought we were gonna do one I didn't have.
Okay. Okay, so we're gonna go over chapter 9 real quick. Okay. Okay, so if we think about a light bulb, we know that if we have an electrode and we connect the 2 electrodes together, we're gonna allow electricity to flow through. Okay, so the battery is providing electricity, it flows to the light bulb, and if electrodes are connected, we're able to get light because electricity is able to flow through. But if the electrodes are not connected, then we can't get electricity to flow through. So that's kind of how like the light switch works, right? Because we connect it, we get light. The room is lit up. If we flip that switch, we disconnect the electrodes. They're not connected. Okay, so now we can complete this circuit by the addition of electrolytes, things that are ionic, because the ions will allow electrons to flow through the solution. Okay, now if the solution has no electrolytes, or if you have a covalently bonded compound, then that situation we do not have electricity flowing through because you don't have ions for it. Okay, so in the case of ethanol is covalently bonded, so it's considered to be a non-electrolyte because there's no ions. When we have strong electrolytes like Gatorade, right, or in our case sodium chloride, or in this case copper 2 chloride, right, we get ions formed in solution, and so electricity is able to flow through, and so we get light. In the case of solutions that dissociate weakly, right, like acetic acid, which is a weak acid, it doesn't completely dissociate. So in that situation, we get a little light, a dim light, because we have just a little bit of ions. available for the electricity to sit there and flow through. Okay, so electrolytes are going to be just the separation of ions. Okay, so when they're in solution, they're able to separate. So when you guys talk about Gatorade or Powerade, all of those guys have electrolytes. So they have those ions that have been dissociated. Okay, so the charges, they have charges associated with it, they're not connected together. Okay. So if we have an ionic solution, we put the ions into water, they separate. They form their plus and their minus ions. And so they allow the transport of electrons to go through that solution. And that's being shown here, right? So these ions kind of pair up, and so that electrons can be paired and shot across so that you get completion of the circuit. Okay, strong electrolytes are going to be those that dissolve almost completely, okay, or completely. Weak electrolytes are going to dissolve just a little bit, meaning that they're not going to break up completely. Some of them are going to still be together. And non-electrolytes don't dissolve at all. They won't separate at all. They're not able to conduct electricity. Okay, so for instance, if you have sodium chloride, you guys have all played with salt before. If you put it in warm water, what happens? Anyone? Yeah, what happens when you put salt in warm water? It dissolves. Yeah. Okay, so we know that it dissolves, right? So as soon as we put it in water, it's going to dissolve. Okay, so it's breaking. What was that?
It also has a laxative effect.
It also has. Okay, that's good to know. So it makes you have
Yeah.
as well too. Huh? Okay.
So if you're constipated, there you go.
Warm salty water. Huh? I'll keep that in mind. Huh? So, thank you.
It has to be warm. It has to be warm water though. Okay. No.
Okay. Now, which way am I supposed to take that in? Just curious. Never mind. Never mind. Never mind. Don't answer that question. It was a bad joke.
We'll leave that for homework.
What? Are you tired, Dr. Harry?
I'm exhausted.
Let's get back. So if you do.
Yeah. So.
It's gonna take a while for it to
Okay, so we know that it's gonna dissolve, right? It's gonna separate into its ionic forms. Now, this is what's really happening in solution. So when we make stuff aqueous, those ionic compounds are gonna be able to separate into their ionic forms, unless they're not able to be dissolved, okay? We'll be talking about that. Okay, and so that's the same thing with copper 2 fluoride. Exactly the same thing. It's able to be dissolved in water. Okay, so here's an example of what really goes on. We throw in that salt. At first, it's all bunched together. As we stir it around, the water will start to isolate the ions. And so water is acting kind of like a home wrench. It goes up to the plus ion and surrounds it. No, 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 you don't need chlorine. You got me, right? And then it goes to chlorine. It says exactly the same thing. You don't need sodium. You got me, right? So it keeps them separated, right? And long as it keeps it separated, they're not able to reform that ionic bond. And that's what water does. So that's how it stays in solution. Okay, now this is the same thing that happens in the case of copper 2 chloride. You add it into water, it dissociates. Water surrounds it, keeps the 2 ions separated. So the copper 2 ion is separated from the chloride ion. Okay, so do me a favor. Somebody who can write on my board. Write the dissolving equation for potassium sulfate. potassium sulfate. Brenda, you gonna help me out? And then Alexis, can you do the second one?
Sorry, what, Dr. Henry, what did you say?
Can you do the first one, the potassium sulfate? So write the dissolving equation. So tell me what potassium sulfate is gonna break down into.
In water?
Yes, in water, yeah.
Okay. Potassium ion, which is K plus.
Okay.
Plus SO4 2 minus.
Okay, so my question is for you. Is this a balanced chemical equation?
No.
No. What do I need to do to balance it?
A 2 on the K, the product.
That's right. So the way that we need to look at this is can I borrow a couple of you guys? I'm gonna turn the camera off. I'm gonna turn the sharing off, and I'm gonna see if I can put the pen on. You guys can see this. Hey, Jay, I need to borrow you. Can you go in the middle?
All of us?
No, I need three. So yeah, potassium sulfate. Okay. So the ladies represent potassium and Jerry represents sulfate. Now you guys, Jerry, hold their hands. Each one of them. No, you guys can't hold hands. Okay, now, so right now, this is the potassium sulfate, right? Without water, okay? Jermaine, I do need you actually. Okay, so now me and Jermaine are gonna be representing water, okay? What's that? You want it to be a hydrogen? No, so we're gonna represent two water molecules. So we're gonna come up and split these guys up, right? And keep them apart. So each of the potassiums are independent of each other. So you're not gonna use a subscript for it because they're separated. You know, you guys are separated. So you're separated from him and yeah. So these two are separated. They're not touching each other. They're not interacting with each other. So that's why we put the coefficient in front of it instead of putting it as a subscript because they're not bound together. Okay, does that make sense? Facing this way. Okay, towards the camera, right? So does that make sense? Okay, good. We want everybody to see our butts. Okay, that's how we roll.
Everybody's
You okay?
Yeah. That's dangerous.
Okay. Okay, so now what would be the ions that would be in the solution of calcium nitrate?
So I didn't understand completely if this is what you were supposed to do, but I put calcium with the 2 charge
Okay,
plus NO3 with the minus charge. Is that what it's just asking to do? And then you obviously combine those two to make the CaNO3 too.
yeah, so but again, they're in solution, so they're gonna be independent of each other.
Oh,
Right?
okay. Yeah.
Okay. Okay, in the case of acids, the same thing is gonna happen, only thing now, it's gonna be the H plus. Now, the thing about the H plus is actually gonna bind to water. It's gonna be attached to water, so it's gonna be H3O because it's kind of clingy. It wants to be clingy onto something. And so it's gonna be clingy on the water after it's separated. So if we have a monoatomic acid such as hydrochloric acid, it's going to be able to separate into its ionic form. We're going to get the chloride ion, and we're going to get the hydronium ion. Okay? And then that's the same thing in the case of nitric acid. We're going to get nitrate and the hydronium ion.
So remember, oh, I'm sorry. Remember when I asked about like how the H2O doesn't get the other H
Yeah.
because it's not used? In this case, you're just showing it's not being used, you're just showing it because it turns into H3. Oh,
Yeah, because it's the H plus, right?
yeah.
And in that case, if it was sulfuric acid, in that situation, it's H2SO4. So both of them are being used. They're both being added onto waters, right? In that case.
Gotcha. Thanks.
Yes, yeah. Okay. Don't know what happened. Hold on. Are you guys still there? Can you hear me?
Yeah.
Yep.
Okay, so again, when we're talking about the acid, this is that example. So that you were just talking about. So here's the sulfuric acid. Here's the sulfuric acid. So if we add it to water, that very first H is going to dissociate with that, with and attach to the water. Okay. The second one is going to stay bound temporarily, but it's going to be happening almost instantaneously. The next one is going to interact with the water, and then it's going to be H3 plus over here, and then we end up with just sulfate. So this here is called a polyprotic acid. Poly meaning many, protic meaning able to get the H plus protein. Okay. And so here's an example of carbon-based acids. Okay. So this is acetic acid. When we put it with water, it goes into what we call equilibrium. Okay. Now equilibrium means that both moieties, both sides exist, right? So your reactant side is present and your product side is present. And so it's present in different quantities, right? At the same time. And it doesn't completely dissociate. So this side here, the product side, is going to be less than what you have on the reactant side. You're going to have more of the reactant still around. Okay. And then here is just generally how we described an acid reaction, although my arrow kind of went haywire again. Okay, so this here is just going to be a generic case for an acid. So for any acid, it's going to be H. That hydrogen defines that acid as an acid. And then the base, what we call the conjugate base. Okay. So strong acids are going to completely dissociate. Okay, so we know that carbon acids are weak acids because they don't completely dissociate. Okay, now when strong acids dissociate, the ions are going to be the major species. We're going to have mostly ions. And the minor species is going to be the acid put together. Weak acids are going to be just the opposite. The acid that stays together, or the unionized molecule, is going to be the major species. And then the minor species are going to be the ions. And this is going to be a poor conductor of electricity, so we're going to get a very dim light. So here's an example. So here's a strong acid. So this is hydrochloric acid. And so we get a strong light. So here's a weak acid. This here is acetic acid, a carbon-based acid. We get a dim light. Okay, and this is just basically showing us what's going on with the table, right? So strong acids, they're going to completely dissociate. And so in other words, we get 70+% dissociation when we have a high concentration of a strong acid. When we dilute it more, we get 100% dissociation. And so this guy is going to be really good at conducting electricity because it forms the ions. And then in the situation, it kind of gives us an idea based upon the length of the arrow. If longer the arrow, is the direction that it's going in, the stronger direction that it's going. So it's moving more towards the product rather than moving more towards the reactant. Hydrofluoric acid is a weak acid. So fluorine is kind of like a bully. It doesn't want to let its woman go, so it's going to hold on to it, not let it go to the bathroom, not let her go do anything. So it's going to be very, very clingy with it. And because of that, it's going to be primarily the major species is going to be the unionized version. These guys put together. Okay. And so in that case, you get very low ionization. So it's going to be favoring the reactants rather than the product in this case. So here's an example, our major species. So in the case of hydrochloric acid, which is a strong acid, you're going to get almost complete dissociation. So you're going to have more ions in solution. In the case of the weak acid, we're going to have more of the unionized compound in solution.
Is this true the further down you go in the group?
Yeah, so the further down you go in the group, typically they're going to be really strong acids. So like chlorine is a very strong acid, right? And then, so hydrochloric acid is a strong acid. Hydrobromic acid is a strong acid. Hydroiodonic acid is a strong acid. So as we go down, they're going to be ready to form those ions. But fluorine, because it's so strong, it keeps a good bond with that hydrogen. It doesn't. It has a hard time getting away.
This goes back to the electromagnetivity.
Yes, it does. Yeah. Okay. So these are some of the 7 most common strong acids. Okay, so we have nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodonic acid, and then we have chloric acid, perchloric acid. Okay. So again, major species is the one that's going to be most abundant in solution, right? Because we have the possibility of having both the products and the reactants in solution. In the case of our carbon-based acids. So carbon-based acids are going to have more of the unionized versions together. So weak acids are going to be the ones that don't ionize well. Weak bases don't ionize well. And then we also know that water is just going to be water. It's going to be primarily just water. So all of those are going to be more neutral molecules. Okay, so write a formula for the major species in solution of nitrous acid. Anytime that you have OUS makes it a weak acid. Okay. So what is going to be the major species? Is it going to be the unionized or is it going to be the ions that form with that acid or nitrous acid?
The unionized?
So the unionized. So we know that nitrous acid is going to be HNO2. Okay, so this is going to be our major species. Okay, that's going to be in our solution. What about in the case of chloric acid?
It would be the ionized, just the opposite.
That's right. So that's going to be H plus or H3O plus. And chlorate. Okay, so those ions are going to be more abundant. Okay, so up until this point, you guys have been writing the chemical equation, except if you already started your exam, right? You've been writing the chemical equation in the conventional sense, right? So we have been writing it as if they're together. But what happens in reality is that they ionize. So if it's aqueous, if it's soluble, it's going to ionize. So really what's happening is they're going to be breaking up into their ionic parts. So in the case of lead to nitrate, we're going to get lead 2 plus AQ plus 2 NO3, because the lead is what's holding it together, holding those two nitrates together. So as soon as the lead lets go, those guys are free, right? So then we're going to have 2 of those free. Okay, same thing is going to happen here with our sodium. So we're going to have 2 sodium ions plus 2 chloride ions and anytime that we have a solid, liquid, or gas, it's going to stay together. So we're going to keep those together if it's a solid, liquid, or gas. We only separate if it's aqueous. Okay, so again, the sodium nitrate is going to separate. Okay, so this here is called the total ionic equation. Okay,
Dr. Henry. For the PbNO3, you put plus 2NO3, and then in the NaCl you separated both. Is it because it's with the metal? Is that what you said?
yeah, because the metal is what holds them together. As soon as that metal lets go of them, they're independent of each other. So there's going to be
Okay.
two of them. Yeah.
So in the case of NaCl, since there's no metal there, or it gets separated. I'm just asking because the way you wrote it, you wrote NO3 as a unit, and then NaCl you
Because-
separated.
Well, because NO3 is covalently bonded together, right?
Oh, okay.
Aren't all three of those non-metals? I mean, all two of those are non-metals, right?
Yeah, nitrogen and oxygen.
So they're covalently bonded together. They're going to stay together. And then
Okay.
in the case of sodium chloride, that's an ionic compound, right? And so they're going to separate from each other.
Okay.
So again, this is called the total ionic equation. Okay, so now the thing about the total ionic equation, we have what we call spectators. Spectators are going to be exactly the same on both sides, right? They have to have the same charge. They have to have the same, chemical symbol. If they're connected to something, they're not considered spectators. So the way I like to think of spectators, have you guys been to parties? Anybody gone to parties before? Has everybody been to a party?
Yes.
Okay, I have one person that's been to a party at Harnell. Okay, we need to fix that. That's a problem, right? Okay. So now, if you've ever gone to a party, you may go with somebody who gets there and just stand on the wall and watch everybody else have a good time. Have you ever done that? Right? So that person is called a spectator because they're literally watching other people interact, other people react. Okay, so in chemistry, we have spectators. So if we take a look at our chemical reaction here, our spectators are going to be those who, again, look exactly alike on both sides of the chemical equations, on the product side and on the reactant side. So here we have the nitrate, that's the spectator. We have the sodium ion, that's also a spectator. So the ones that are actually reacting are going to be the lead ion and the chloride ion. So when we talk about the net ionic reaction, we get rid of the spectators. So we're going to get rid of our spectators. So in this case, we're going to have just lead making our lead to chloride. Okay? You guys see that? Questions? Concerns? Cash money? Okay, so the way that you want to do this always, the first thing that you want to do is start off with your conventional equation. Make sure you put the symbol, the state that it's in. Is it aqueous? Is it a gas? Is it a liquid? Is it a solid? We know that anything that's aqueous can be broken down into its ionic components. Anything that's a solid or liquid is always going to stay together. Solid, liquid, or gas is always going to stay together. Okay. We want to make sure our equation is balanced, of course, with our coefficients, and we want to make sure that when we do that separation, if it's a metal keeping it together, they're going to separate into their ionic components, right? Okay. So it says when a strip of magnesium metal is placed in iron, it says placed in an iron 3 chloride solution, magnesium chloride solution results, and iron forms. Write the net ionic equation for the reaction. So what is going to be the conventional equation for the reaction?
So magnesium plus the iron 3 chloride.
Okay, so we have magnesium. So it's magnesium metal, right? So it's not going to be an ion. It doesn't say ion, so we know that it doesn't have a charge associated. So we're just going to put magnesium metal. Is that going to be a solid, liquid, or gas?
Solid.
It's going to be a solid. Okay, and it's reacting with, you said, iron 3 chloride. So what is the chemical formula for iron 3 chloride?
So you got Fe
Okay,
and 3 chloride.
okay, so FeCl3. And it says solution, so we know anytime it says solution, that is going to be
Aqueous.
aqueous. And then that's going to yield they're going to make
Fe. Right? One of them's Fe.
that's going to be solid, liquid, or gas, or aqueous.
Solid.
Our other product,
Magnesium chloride solution.
okay, chemical formula,
MgCl.
Cl what?
I think it's 3.
Nope. What is the charge on magnesium?
Positive. 2 plus.
It's 2+, that's right, it's 2+, so we know that chlorine is a 1-, so I'm going to need 2 of those to balance it out. And that's going to be AQ, right?
Yeah.
Okay. So that's going to be our conventional equation. Is it balanced?
No.
No, what do I need to do?
You put a 2 in front of the FeCl. And then you put a 2 in front of the Fe. And then you put a 3 in front of the MgCl2. And then you put a 3 in front of the Mg. I don't know if that's right.
That's
I
right.
did it in my head. Okay.
Good job. Okay, so now we're going to do the total ionic equation. Okay, so this is a solid. So what do we do if it's a solid? Can we break anything down? So if it's a solid, liquid, or gas, do we do anything to it? It's a 50-50 chance, either yes or no.
Does not.
Okay, So we're not gonna do anything to it. We're gonna write it down as it is. Okay? So we have FeCl3 aqueous. Can we break that down to its ionic compounds, components? Yes or no?
It's aqueous, so you can break it down.
Okay, so we're gonna break it down. So we get 2 Fe. And then how many chlorides do I got? It's 2 Fe, 3 plus.
F3.
So we have 3 multiplied by 2, right? So then that's a total of how many?
Oh, 6. Yeah.
So we're gonna have 6 chlorides. Okay, then on the product side. Well, we have FeS as a solid. So I'm just gonna write it down as it is. And then we have magnesium chloride solution. So is that gonna break down into its ionic components?
Yes.
Okay, so we're gonna end up with 3 magnesium, 2 pluses. And 6 chlorides. Okay, now
So nothing changed?
there's something that changed, right? If we take a look at it, do we have any spectators?
Your iron?
Well, is it? Because this is iron 3 plus, right?
Oh, the other side's not 3 plus? Because
That's
it's not needed as a charge.
That's right.
So your 6Cl is your spectator.
That's
And
right.
your... Did you not put the 3Mg plus 2 on purpose in the front?
Yeah, because it's a metal,
It's
right?
alone, right? Yeah, it doesn't need anything.
It doesn't say that it's an ion. If it said an ion, then we put a charge on it. But since it's not an ion, it stays with no charge, right? Okay, so then these are our reactants. So when we break it down, we just have our net ionic equation is going to be Mg, 3Mg S plus 2 Fe 3 plus or it's going to yield 2 FeS plus 3 Mg 2 plus. And that's it. Okay, so you guys see what I mean by it has to be exactly the same on both sides?
Yeah.
Okay. Okay, I think this is a great stopping point because my brain is about to fall off. I guess I meant my head is about to fall off, not my brain. So Friday, I am gonna have to cancel lab. I have something I have to take care of, and I can't get out of it. So there won't be lab on Friday. I'll make it up to you by having a special review for you guys. Okay?
Wait, is this for heart? No.
For heart nail, yeah, because you're the only class I have on Friday.
What about Thursday, Dr. Henry?
What about Thursday?
Uh-huh.
Thursday, we are gonna have a class where we're gonna have a special review. So,
Okay.
okay. Okay, and if you guys are on Friday, if you guys want to come on Thursday night from 6 to, I'm sure we can squeeze everybody in. So if not, we could find a room somewhere. Okay, and I'll send an email tonight to remind you guys of that and tell the rest of the class that didn't show. So. Okay, you guys have a good night, and then I'll see you on Thursday.
Okay, good night.
Okay.
Will you share the Zoom link for Friday class?
Will I share the Zoom link for Friday class?
Uh-huh.
Yes, I'll share it with you
The
guys.
special review?
Yeah.
Okay, thank you.
Okay, I have to figure out a time because I'm gonna be occupied most of the day, so
Uh-huh.
I won't be free to be able to do it. So,
Okay.
yeah, that's why. Okay, I'll see you guys later.